Yeah, thanks a lot for the invitation. So yeah, the talk of today is related to somehow with my background. So my background is aerospace in general. I care a lot about things that fly. So this is kind of a way of improving the models that we have now for computational fluid dynamics. I'll first let me start with some motivation or some latest short summary of my group, things that we do. So usually my group is kind of divided into two branches. One is more related to physics and theory. So it's more understanding like in very simple geometries, try to understand what the flow does, in particular when the flow becomes turbulence, or usually if the velocity is slow in a flow, it looks smooth and organized as the laminar flow, but that in most practical applications that doesn't happen. The flow will look more like what the picture that you see on the left. This is a visualization of the velocity. If you were able to see the velocity on that turbulent flow, you will see that this pattern looks like multi-scale and it's very chaotic. So we try to bring new tools to understand the physics of this problem. And the other thrust in my group about research is about taking that we learn, those physics that we learn, and apply them to turbulence modeling, so yes, to computational fluid dynamics. And that's the talk today is about what you see on the right. It's about how to introduce also new tools and new physics to improve the models that we have to make predictions. So in general, what we want to predict is the forces over some kind of vehicle, like could be an aircraft, or could be a rocket, or could be also like automobile. So it could be something to that. So the talk today is going to be focused mostly on that. But I also wanted to mention that the motivation of why we develop these models and how they are implemented is in a way informed by the physics that we learn in simple cases. And this actually talk will show that in a very clear way, probably. This is a movie, in case you can see that well. So this is a simulation of a flow that is changing direction. So it was moving in the horizontal direction and now it started to move vertically. And this is a very simple setup in geometry, but we also use like very large scale simulations to try to extract physics from this type of problems. Okay, let me also acknowledge the people collaborating in this project. So people in my group, some students, Yuan Ling, Gonzalo, also Jane Bay from Caltech, and Conrad Gott from Boeing. And I also want to acknowledge the funding for this project is NASA, Boeing, and NSF, and also partially from Stanford University through a summer program. So what is the problem that we are trying to solve? The problem is motivated by, in a way, commercial aviation, but it will also apply to space or any other type of industries. But the kind of aviation is kind of very obvious. So if you think of an aircraft, usually during the design of the aircraft, what you need to do, you need to compute what is called the qualities of an aircraft. So what is a quality? Quality could be anything related to how much is the drag of the aircraft, of the lift, or the moments, the stability. And that goes across many different disciplines, could be fluid mechanics, materials, even all the electronics. But what is important from our point of view here, that I am going to be worried about the aerodynamics, is that these qualities, most of them, the way they are demonstrated, like the way they are shown to be what they are, is through a flight test. So flight test means that either we have a wind tunnel experiment or we literally build the full aircraft and we test it. And obviously that's a problem because it's very expensive and it's slow. It takes a lot of resources. So the goal, or what the industry is trying to move in a direction that is called certification by analysis. Analysis here actually means simulation. So we just don't want to build the aircraft. We just want to demonstrate through some numerical simulations that we can predict actually what is going to happen without building the aircraft. And that is something we can do already. The challenge is that the uncertainty of the errors that we get in the models, computational models that we have are high. And if we really want to replace a flight test by this certification by analysis, we need to maybe go to 1 or 3% error in the quantity of interest that we care about. So the idea is not to completely replace experiments, but ideally we would like to minimize the amount of experiments that we need. So maybe 1 or 2. And also the idea is not building the aircraft. At the end, you have to build the aircraft and test it. But we would like to be almost sure that once that we build the aircraft, there is going to be no surprises. Like we are going to get what we already thought, and we don't need to iterate on the design. That would save a lot of money and also time. And this is kind of the problem. This is the number of wind tunnel experiments required for designing an aircraft. And in the 70s, it will actually take 70 of the order of 70 wind tunnel experiments. That was a lot. And then that, because of computational tools, that has been dropping. So less wind tunnel experiments. And those, they were replaced by computational fluid dynamics. And I also like to mention like this rule of thumb of the cost of doing either a simulation or actually testing the aircraft in the wind tunnel or actually testing that for real. So 1 hour of computational fluid dynamics will take 1 day and it costs like $1,000. And then essentially you go up by an order of magnitude. Like if 1 hour of wind tunnel would be like $10,000 and it will take a few months. And then 1 hour of testing the full aircraft, it will take 100K per hour and it's 1 year. So we would really want to be as much as possible in the first point. We want to test computationally as much as we can. And ideally we want to have 1 wind tunnel experiment maybe, or a few, and maybe on final flight, the final aircraft. And this is in a way has been achieved by computational fluid dynamics, but you see the trend in the 90s, the number of wind tunnel experiments was 10. And then in the 2000s, it remained stuck there. So it's been like 24 years and it remains in 10. And the reason for that is that there was a bottleneck in what the models, computational models for predicting the aerodynamics, what they can do. So the goal of what part of I do, my work, and what we do in my group is we want to just reduce this number and bring it to just a few if possible. Okay, so what is the challenge? I mean, why the simulations that we have, why they don't work so well? Why they don't give us very low errors? I'm using this slide to motivate in that. So the problem is that if you think of the flow over an aircraft, there are like different type of flow regimes, that things that can happen. And these are kind of conceptual. This is conceptually what the flow could do. And sometimes the flow over the aircraft, it will be shaped in a 3-dimensional way on the mean. Sometimes the flow is smooth and will transition to be turbulent. What happens also is the region where the viscosity is important, and that's the turbulent boundary layer is very thin. It's easy, difficult to resolve. There might be shock waves. So these aircraft, they are transonic, so they will generate a shock wave over the wind. It's also difficult to predict. And there might be separations. The separation is that you have a recirculation bubble in some regions of the flow. So not all of these are happening at the same time, but at some point during the flight envelope, they might happen. And we have models that are good at predicting one of these effects, but there is no model that is able to predict all of these at the same time. And so that's what we are trying to do. So what is the challenge? So in a way, the challenge is we want to have a model for computational fluid dynamics that is able to account for all these type of flow features. So you have different flow features, and we want to account for them, and maybe more. This is just an example. And then we have some constraints on how we can design this model. This is the goal on imposing these conditions. So I'll define later the terms of what I mean by closure model in this context, and large-scale simulation. This is the framework we are going to use to design the computational model for the aerodynamics. But essentially, we want to be able to account for these different flow features. That's the first point. Imagine that I'm missing some physics, and I realize later, okay, my model should be able to capture some physics that I don't have here. Then I should be able to scale up the model to include those. Then these simulations, obviously, we use a computer to integrate the equations, and those equations, they have some numerical errors. And the model has to be aware of those errors and has to be consistent with the numerical errors. And ideally, we'll also like to have some confidence in the prediction. So it's not, I don't only want to, for example, get the forces over the aircraft. I would like to get some confidence of what the model thinks, if that prediction is good or bad. So that will also play a big role. And the last part is it has to be applicable to complex geometries. In the sense that I don't know a priori what is the geometry. Here I'm using an aircraft to illustrate the case, but ideally the model is not designed for this type of geometry of an aircraft. It could be applied to an aircraft, to a rotorcraft, to a submarine, to a drone, to a car, doesn't matter. So the model shouldn't assume anything about the shape of the case. So that will also impose some constraints in the way we can design the model. Okay, so this is what I'm going to talk about. The model is called building block flow model, and I'll explain why is that. And I'm going to talk about the assumptions. The building blocks are some data that I use for training the model, and the model is going to be implemented using machine learning tools. This one is neural networks. And then I'll show a validation case of the model. Once that the model is trained, this is an aircraft that is used by many people in the community just to test different models. And the model is developed in 2 steps. That's why there is a second bullet point that looks very similar, but is an extension of the model to capture physics also far away from the solid boundaries. I'll explain that. And then I'll mention some limitations of the model. So we have a few proceedings and a few papers that are related to this, but if any of you in particular are interested in the work, you can just Google for the building block flow model, and probably this will show up. This presentation is not going to be super technical, it's more like high level, but if you want to know about more technicalities, then you can go to these places. Okay, so the first thing that we need to talk about is I want to compute what the air is doing over an aircraft. And the question is, how expensive is that computationally? So let's try to discuss that, because that's in a way, that's why we are going to need to have some simplifications in the way we compute the flow over the aircraft. So imagine that we have our aircraft, and I'm going to look at a section here in the wind. So physically, what is happening? There is some air. This is a cut of the wind over the wind. There is air coming from far away. We are in a frame of reference of the aircraft. The flow is smooth, it's laminar, and then almost immediately it's going to transition and become turbulent. So it means that this is going to generate eddies of many different sizes, many different scales, and this is going to be the turbulent boundary layer. So this capturing these motions, that they are multi-scale and very chaotic, is important because they are affecting the lift, the drag, the moment. So the way these motions move is important. So in a way, our computational grid should be able to resolve these motions. So let's zoom in and look at these motions. And we want to estimate how is the size of this motion. So we want to estimate 2 things. One is, what is this region close to the surface where the motions become turbulent and chaotic? That's this delta. And then this problem is multi-scale. So we have some of these eddies that they span across delta, and then they have some of them eddies that these are very tiny. And the ones that are the tiniest is the eta, is the Kolmogorov scale. And you can make just an estimation for a typical aircraft. You just need to use how much dissipation you have and the typical velocity of the aircraft. And you get that in this wall normal direction to the surface, the ratio between this delta and the smallest eddies could be of the order of 1,000 or 10,000. That's essentially will give you a feeling of how thick is this delta compared to the smallest eddies that you will get, 10 to the 3, 10 to the 4. And this is only in one direction. So now I need to account for the fact that this is happening in the 3 directions and it's happening all over the area of the aircraft. So that means that my computational grid, I have to set it such that it needs to resolve the smallest motions. Okay, so just using this, I can make an estimation. Like imagine I want to resolve my equations. The equations are known. The equations are conservation of energy, mass, and momentum. There is no problem with that. The question is how many grid points. I need to be able to see all the scales of the problem. So what I'm showing here is just the equation. This is a particular conservation of momentum, but there is no problem with that. It's more a problem of I need to be able to see all the scales. Otherwise, this equation is not going to be accurate. There's going to be errors. So you can make a number, how many points I need for a typical aircraft. So the number of points that you need, you integrate this estimation over all the area of the aircraft. And in general, you will need 10 to the 17 points. So if you think about this is actually quite kind of a very massive number. So this means that imagine I want to look at the density in each point in my grid. I take the density at each grid point. That's going to be 100 petabytes per quantity at one time. That's actually very massive. And also, it's even worse than that because imagine I want to solve this problem in a computer. So I need to fit the problem in the computer. So the computer should have enough memory. And also then I need to crank the numbers. And if you make some estimations about that, it's impossible. So even if you combine all the supercomputers together that exist now and you put them all together, the problem doesn't fit. I mean, it doesn't fit in the memory because it's so large. Even if you imagine that it fits in the memory, and then you say, okay, how long it will take to solve the problem? It's essentially a ridiculous number. It will take thousands and thousands of years. So it's not a matter of, oh, maybe the computers will get faster in 10 years. No, it's not that. They will never be able to solve this problem. There is so many degrees of freedom. There are so many grid points. So we need to think about this problem in a different way. That is the opposite way. It's like, okay, imagine what can I afford? So what I can afford is a grid that maybe could be of the order of millimeters. And if I use a grid that is of the order of millimeters, then I will need 10 to the 8 points. 10 to the 8 points is 100 million points. Like any quantity I want to save in my hard drive, for example, again, the density, it will be 10 gigabytes. That's okay. And then if I have a supercomputer, it doesn't need to be very large. It's a supercomputer that has 1,000 CPUs. It will take 1 day or maybe a couple of days to solve this problem. So this now looks more useful because now I can actually put this in a computer, wait 1 day, and have predictions. These are order of magnitude, so it could take 1 week, it could be more or less points, but the answer is that, I mean, we went to before it was absolutely impossible, there's no way, to something that is possible. So this is the grid that we can afford. What is the problem? I mentioned to you later that the smallest motions that we have in the flow are very tiny. They are usually microns. So these motion, those very small motions, they are not here. They are not captured, but they are important. They are important because they affect, this is a nonlinear system. Everything is coupled, all the scales are coupled with everything, and they will affect the forces over the aircraft. So if I try to solve my equations in this grid, the errors are going to be huge. So what do I need to do is to compensate for that. And this is where the closure model problem comes into play. So my idea is, okay, I'm going to solve my equations that are conservation of energy, mass, and momentum in this grid that is very coarse. But now I'm going to have a model that accounts for the fact that I'm missing the smallest motions. And when I look at that, usually conceptually, this is divided into 2 models. The models that are far away are called a grid scale model. It accounts for these small eddies that are below the size of the grid, far from the boundary, the surface. And then there is technically another model that is called wall model that is accounts for the effects of those small eddies exactly at the boundary of the wall. The way grid scale models work is like they use usually some local information from the grid that is resolved, and they try to estimate, okay, what are the motions that I don't have doing? So you need some physical assumption about that. And a wall model, the way it works, it will gather some information from some few grid points far away from the wall. It will get the flow state, its density, velocity, temperature, pressure, and with that, it will make an estimation of what are the forces at the wall. This is in particular the wall shear stress. So now if I want to run a simulation using this grid and I want it to be accurate, I need to have these 2 models. I need to, and the way of creating a model, I need to have some physical assumptions about those scales that I'm missing. So in this talk, I'm going to show you these 2 models, but I'll go to the first step. I'm going to tell you about how I do the model that will predict forces at the wall. And then I'll tell you about the other model. And the framework that I use is large eddy simulation. And it's called large eddy simulation because only the large eddies are resolved and the small ones are modeled. And it's called wall model because also close to the wall, we account for the fact that those small eddies are not in the, resolved by the grid. So that's why it's called also wall model large eddy simulation. Okay, but there are other frameworks that are also perfectly fine. It's just that it happens to be the one that I use in large eddy simulation, yes, LES, for sure. So let's talk about the part 1, how I create the model. And most of the things that I talk about this wall model are actually applicable to the second part 2, the grid scale model. It's the same principle. It's just easier to explain for a wall model. So the model I'm referred to as is BFM. And I'm going to show you the equations of the model, the assumptions, the building blocks, that is the data I use for training. It's going to be implemented in a neural network. I'll show you the neural network and then how I generated data for training that. This is maybe the most technical part, is just the equations I'm solving. There is nothing special about this. I use conservation of mass, conservation of momentum. There is also conservation of energy, and we show that here. What is important in these equations, the U are velocity, rho are densities, and the bar. I'm using this because now this is kind of a coarse-grained version of the system because my grid is very coarse. The grid is an example of how an actual grid will look locally close to the wall is like this. It follows like a Voronoi grid. But there are two terms that I need to model in this equation. They are highlighted in red. One is the grid scale model that I mentioned before. It is the red smaller than the grid. And then there is the stress at the wall. The effect of those eddies, the footprint that they have at the wall. And this tau wall enters into these equations as a boundary condition. So one model is trying to predict the boundary condition for these equations, and the other model is correcting the conservation of momentum. So what is the idea now? I need to close these two terms. I need a physical assumption about how to compute these terms. And this is the high-level idea. The idea is the following. The idea is that I can think of a collection of simple cases. These are cases like the ones that I show you here. They all look like two walls, and there is a flow confined between those two walls. And I can play with a pressure that will accelerate the flow in different directions, and I can move the relative velocity between the walls. And when I do that, what you see here in red is on average like the mean flow direction, the mean velocity. And there is a case that I have like a free stream, like all the flow is uniform in one direction. The second case is like laminar flow, so there is no turbulence, everything is smooth. And then the other cases, they have a turbulent flow, but the mean profile will change. In some cases, will have some change direction. In some cases, it will go to zero derivative at the bottom wall. And in the last case, is trying to show that it could have some two components and some three-dimensionality. So the assumption is that I can use these building blocks to learn the physics that I'm missing when my grid is very coarse. And if I learn that here, that I can actually, when I have a complex case, this would be a full aircraft. The idea is like, if I look locally at what is happening in the aircraft, I can always map that to one of these cases or a combination of cases. So that's how the model works. So that's kind of the assumption. The assumption is that I can break down a very complex case into very small pieces. And locally, it should look like one of these cases. And the reason for that is because these cases, I can actually have experiments or high fidelity data that I can use for training my model. And I know the correct solution in these simple cases, but I never know the correct solution in the aircraft or a complex case because that's what I'm looking for. So I cannot use that for training a model. So that's essentially that step. And that's these two here are the main assumptions of how the model works. So let me talk a bit about what is this collection of flows. And that's what I call building blocks. And that's why the model is called building block model. So these blocks are intended to represent different physics. I kind of mentioned this already before. The first case is a free stream or laminar flows where there is not important pressure gradient. And the cases of the two cases on the bottom left is the effect of pressure gradient. It could mimic the fact that the flow could separate or that the flow is accelerating or decelerating in one direction. And the last case is what happens when the flow has some three-dimensionality or is statistically steady. So even in time, it's changing. And these are just kind of the different types of cases. So it doesn't mean that I have 6 cases. I have many more. It's for each of these cases, I have many simulations. They are very high fidelity. And I know the answer to these cases with like all exact accuracy. In total, if I account for all the cases that I have, is of the order of 500 cases. And these cases are solved using what is called like direct numerical simulation. It means that I resolve all the scales of the flow. So from the very large to the very small scales. So I don't need to assume anything about the small scales because I'm actually solving them just using the Navier-Stokes equation. And this database is of the order of 1 petabyte, more or less. And the way we generate these cases, there are some non-dimensional numbers that they control these cases. So we need to make sure that we sweep across all the non-dimensional numbers to go through all the possibilities and all the combinations, and discover a wide range of combinations. And this will generate the training data. This is what my model is going to learn to be very good at predicting these cases. And now I want to apply that to a complex case. And this is how, now we move to the architecture. So this is how the model, once that the model is trained in those previous cases, this is how the model will look. Imagine I take a small, zoom in a small region close to a wall. This blue region is the grid. And then in the grid, I'll collect some information. In this case, I collect some velocities, distance to the wall, and accelerations, and then I will use some inputs. And then these inputs, what matters is not the input itself. What matters is like the non-dimensional numbers that you can create with your input. So the units shouldn't matter. And the way of getting non-dimensional inputs, you have to cancel out the units. So you can think of how many parameters you have. We have distances, velocities. This mu is the viscosity and ratio of density. And with that, we create a set of inputs. In this case, we have 6. And those inputs are going to be passed to a predictor. So the predictor is actually what makes a guess, a regression about what should be the forces at the wall. So at the wall, the force is a vector. So that's the output is still non-dimensional. And it will tell me the stress at the wall in a non-dimensional form, and also an angle, like with respect to the velocity far away from the wall, in which direction that the stress is. But the other component of the model is that before that, there is a classifier. So this classifier, what it's doing is trying to detect if the flow in this region looks locally similar to one of the building blocks that I had before. So it will give me some classification. For example, it will tell me the flow here locally looks like this given percentage of separation flow. That's one of the cases I use for training. It also will look like some percentage of CPG's zero pressure gradient, then adverse or favorable pressure gradient, and it will give me a complete classification. And that information is used for a blending of the predictor. It will combine the information from the building blocks where I know exactly what is happening and I know the scales that are missing, and it will help me to get the prediction. And the last component is a confidence. As I mentioned before, I also want to have a confidence, and the confidence is based on how different is the training data that I use for creating the model with the actual input that I see in a real case. I can compare those two, and I'll make some comments later, and that will give me a confidence. So this is essentially 3 components. I'll discuss a bit more about the inputs. I have 6 inputs. The reason for that is because I at least need 6 non-dimensional numbers to be able to distinguish between all my building blocks. And this is something you can do by applying the Buckingham-Pi theorem. It will tell you you need 6 groups. Those are not unique the way you define them, but this is the one that we found that they work. I'll give you some small interpretation of what they mean. The first 2 inputs, they just tell me like locally how much there is a scale separation, like how fast is the flow compared to the viscous effects. So it's a ratio between inertia and viscous effects, and that's usually referred as a local Reynolds number. And they also allow me to detect the shape of the mean velocity profile. This one is an angle. It's a relative angle between those velocities. They don't need to be parallel, and that will measure 3-dimensional effects. These ones are related to acceleration. So this A and the gamma dot is accelerations of angles and velocities. So that will allow me to measure inertia effects, like unsteady effects. And the last one, this is a relation of the amount of kinetic energy of the fluctuating flow, because this is a turbulent flow is fluctuating, compared to the mean kinetic energy. So this is helping me to detect if the flow is laminar or if the flow is turbulent. So this kind of physical interpretation of what each one means. And then we will pass them all here. And this predictor, classification, and classifier are deep feed-forward neural networks. I have some details here of how they are. They are of the order of maybe 5 layers with 30 or 20 neurons per layer. The classifier is a Bayesian classifier. I don't emphasize much a lot this architecture because I don't mean that this is the best. It's just we essentially try different configurations, and we saw that this one was okay, like it was giving us good performance. And then finally, again, going back to the output, what I mentioned before, one component is just the magnitude of the stress at the wall, and the other one is a relative angle, because the stress at the wall is a force, and that it has direction. So we also need to know the direction. Okay. So this is kind of overview of all the components, and kind of a small justification of what they do, each of them. So the predictor, if we zoom in and I open that box for you to see how it looks, it is actually not a neural network, it's a collection of neural networks. So I have a collection of models, and each model is very good at predicting one of the type of flows that was designed by one building block. So I have a neural network that is very good at predicting zero pressure gradient. The other one is favorable, the other one is adverse. And every time that I have an input, I will predict all the possibilities of type of flows, and they will give me a prediction of what is the force at the wall. And then I will blend that prediction with the classification. The classification will tell me you have 80% of CPG and 20% of FPG, and it will blend that. And that's how the prediction is done. So in a way, I'm predicting all the possibilities at the same time, and then I blend them according to the classification that I have. That is the probability that I think that the flow actually looks like that in the real case. So that will be the predictor. Then the classifier, essentially, this is the way it looks, the way it was trained and generated. I took all the simulations that I have from the building blocks. I fed them to the classifier. I know the answer for these cases, how they should be classified. This is a supervised learning. And then I train to make very good predictions of the classification. And every time that you train a classifier, you can look at what is called the confusion matrix. So this is a way of measuring the performance of a classifier. So what you see here is the different type of flows. It goes from free stream to unsteady, going through all of them. And the vertical axis is the true class. This is what they really are. Then the horizontal axis is the predicted class. It's what the model thinks they are. If we are in the diagonal, it means that the classifier would work well. If we are off the diagonal, it means that the classifier actually failed. And this percentage is the percentage of the total number of samples. So in a way, diagonal correctly classify point, off diagonal misclassify. This is just a way to show that in general, the classifier works well. So most of the time it's able to really tell what is the flow, at least from the point of view of the training set. So it's a clearly defined problem. Okay. So now let's go back to the last component. The last component is the confidence. So I told you, I don't want just a prediction. I want to know how confident the model is about that prediction. And how to do that? There are many different ways. The approach we use is how close the input is to the training set. Let me show you this. This is just a sketch. It's not because the input is high dimensional. It has 6 dimensions. But this is conceptually how it works. Imagine that I have only 2 inputs, input 1 and input 2. And imagine that my training data contains these yellow-orange dots. So this is the data I use for training the model. Now, and that is simple cases. Now I'm going to deploy my model in a complex case. It's an aircraft. It's very new geometry. My model has never seen that geometry before. So every time that I give an input to my model, there are 2 cases in general. Either the input in the real case is within the cloud of training data. So then my model is going to tell me, okay, this input looks very similar to something I've seen before. So I'm going to give you a very good confidence. I think that I can predict this case well. But imagine that the input is actually very far from the training data. That would be like this point here. Then the model will give me low confidence. The model will give me a prediction, but it will also give me a warning saying, I've never seen this before. I've never seen this kind of input before. So I'll give you a prediction, but you have to be careful because maybe that prediction is not reliable. And the way of doing this, you can define kind of a distance in a high dimensional space between the input and your training set. And you can then check papers for technical details, but this is the main idea. So with this, all the components are ready of the model, predictor, classifier, and confidence. And now the next step is that we want to validate this in cases that it wasn't trained for. Let me go to this model validation now. So we have tested the model in different cases. Some of them are semi-simple, like channels, but also pipes, flow over a flat plate. Also more complicated cases, like they look kind of like an aircraft type geometry. And I'm not going to show the simple cases, those are in this paper. I'm going to focus on the most challenging case, that is the full aircraft. So I'm going to talk about this case. We are going to compare with experiments. So these are experiments done in NASA Langley, and this is the NASA Common Research Model for high lift. So this is kind of an aircraft that is landing, so it's high lift. And this is how the experiment looks. So it's half of the aircraft. This is a wind tunnel. So this is the setup of the case. We are running a simulation. It's also half of the aircraft. The number of points that we have is like 40 million bit points. Again, we are choosing this because it will take 1 day using 2,000 CPUs. And this is a Reynolds number of 5 million, and it's low Mach number, meaning the compressibility is not important. So now we are going to simulate this case using large scale simulation. And we are going to do two things. We are going to run a reference case. This is a case, I'm calling these traditional models. So these are models that they already exist. So we just took models that they already exist, and we took the best practice for these models. The people already look at some ways of refining, and they look at some particular models, and they concluded, this is we got information from the people from Boeing. They told us this model, that is dynamic Smagorinsky model, with this Sagritte scale model, with this model at the wall, that is called equilibrium wall model, is probably the one that is used the most. I won't discuss much about that, but it's a simplified ODE close to the wall based on some equilibrium assumption. This was the best practice. This is the one giving us the best result for this type of grid. And we are going to run exactly the same case, but we are going to replace the wall model. And instead of that, we are going to use our model, like building block flow model for the wall, and then compare the results. So now we are replacing this wall model with the building block flow model. The part of the Sagritte scale model remains the same. This is just a visualization. So you can see kind of, I told you that we could resolve the order of a few millimeters. So still, most of the features, the larger scale features of the flow are resolved. This is if I play this again, this is a simulation of the forces at the tau at the wall. This is a top view, so you can see the flow. It's a very turbulent flow, so it's changing in space and time. Okay, so these are the results that we got. We look at three quantities of interest. The lift, that is the vertical force sustaining the aircraft, the drag, and the pitching moment, which is the moment that tends to be even more sensitive because it depends on the distribution of forces. So the dash is the experiment that I was mentioning in the wind tunnel. The close orange is the building block flow model, and the open blue is the previous best practice. So in general, what we can see, in most of the cases, our new model can improve. So it tends to push the solution in the correct direction. It's still not perfect. There is only one case where that doesn't happen. This plot, it contains the lift, drag, and pitching moment coefficient as a function of the angle of attack. So for different angles of attack, then you will get different answers. And then you see that at low angle of attack, the lift is slightly off. So that was the only case where the model didn't perform better than what we had. But in the other quantities, it was better. So we did actually some investigation of why was that. And we realized that changing the model to predict the forces at the wall wasn't enough. We needed to actually change all the model, also the ones that predict the effect of this model is far from the wall. So that was one conclusion. But something that we can do that you couldn't do with previous models is to look at something like this. On the left is the prediction of the model, the stress at the wall. And on the right is the confidence. So I told you that the model can also give you this confidence. So this will we can look at the function of the space and over the surface of the wind. We can see when the model thinks that is doing a good job or is not. So here, sometimes in some regions, is 0% confident. Again, that means that doesn't mean that the prediction is wrong. It means that the model has never seen an input like that. So you should be careful about the prediction. In some regions, it's actually close to 100%. So I think that this is very useful because then we can use this to kind of inform future versions of the model. And I can also try to understand why this is happening. So there is like a low confidence region at the leading edge. And we can understand why is that, because there's a boundary layer that is very thin, so that we cannot resolve the flow. Then there is these other black regions at the trailing edge. We know that those are regions where separation happens. We know that from the experiment. So this is an indication that maybe these simple cases that we use to train the model to capture separation maybe are not the best. Maybe we need to revisit those. So this is essentially what it's telling us. So this is useful in that sense that now we know where the model is failing a priori at least, and then we can try to think about that. And this can inform a new training set. We also use this for refining. So maybe now I can run a new simulation, and these regions of zero confidence, I could refine my grid and see if the model will now have a higher confidence. Maybe the grid was so coarse that it's really not able to resolve any energy in the flow, any scales at all, so then it will fail. So again, can use this in two ways: to improve the training data or to refine the grid and see what it happens. So the last part is actually very quick because it's essentially the same idea, nothing changed. But remember, I told you that we need two models, one to predict the forces at the wall, and that is the one that we replace. But we also need another model that is to predict the effect of the small eddies far from the wall. This we didn't do at the beginning because it's more challenging, but then we realized that we need it, especially if we want to get to those very low percentage error. And the idea is exactly the same. It's the same architecture. The only thing that is different now is that now we could move far from the wall. We can have a grid point that is very far from the wall. And now the inputs are this I here, that these are invariants of the velocity gradient tensor. So we think that the velocity gradient tensor is what matters at each point, but to make it invariant under rotation and translation and Galilean invariant, we compute these invariants, and that's the input. And it's a similar structure. It has a predictor, and it has a classifier. And this was like one of the first versions that we did of the model. Now we are working on a second version that this model will predict what is the effect of the missing scales at some point in the grid through an eddy viscosity. This term is a way that we have to compute the term on the right-hand side that we are missing. And it will also give us some confidence and some classification. And again, this is trained on simple cases. So I emphasize that. So this model has never seen an aircraft. It's just trained on simple cases. And now these are the new predictions that we got. We still, they were kind of consistent in the way that there is still room for improvement, but this version of the model wasn't trained in as many cases as before. Now we are starting to retrain the model in all the cases we were using before for the wall model, also now for the grid scale model. So what we expect, our expectation is that when we do that, hopefully we will be able to see improvements in this. There were some improvements though. The pitching moment now was much better, and at angle of attack, the lift was much better, but still we were not able to fix the lift at low angle of attack. That didn't work yet. So we had kind of understood why is that, and now the new version of the models, we're trying to fix that. But as I mentioned before, I want to emphasize that we were very happy that the model was able to predict that, because the model has never been trained with an aircraft or with anything that looks even similar to an aircraft or a wing or an airfoil. So it's a general model. So if we are able to make predictions in complex cases, it means that we are kind of extracting the correct physics from the simple cases and introducing that in the complex case. So that's the goal of what we are trying to do. Okay. This is just a cut through the wing to see the pressure. And we were trying to explain why the model improves. We want to make sure that it's not by chance. So we look at some more quantities. The blue is the building block flow model, and the crosses is the experiment. So we are not able to still match exactly the experiment. There are errors, but you can see there is a big improvement with respect to what was done before. And I also want to emphasize what was done before is what the people from Boeing told us. This is the best we found that we could do. We took that, we tried to improve from that, from what they thought it was the best. So it's not perfect, but at least we move in the right direction. Okay, this is it essentially. That's the model. We have more examples that we have been testing, but I think that this was the most interesting one. And I have just one more slide about limitations. I wanted to say there are a few limitations of the model. This model I told you is trained on some basic units, like these templates, building blocks. It's unclear what are those building blocks, what are the best ones, if I need more, or I could use less, how many. So there is some kind of thinking there. Then there might be as any problem, interpolation, extrapolation, especially when you use machine learning, could be a problem, especially extrapolation. Interpolation, we are confident that the model will do okay, but extrapolation, you never know. Then the model doesn't account for many physics. We just introduce some of them in the building blocks, but there are things like shock waves, compressibility, chemical reactions, multi-flow, all other type of separation. The model cannot capture that. But the idea is that we could introduce those in the future. That's what we are trying to do. And then there is a confidence score. Still, the confidence score is just a way of knowing if the training data looks similar to the input in a real case, but it's not uncertainty. It's not really, we would like to have an uncertainty in the prediction. It's not exactly that. It's kind of an uncertainty of what compared to the training data. Then this model is kind of tailored for a particular numerical solver. If we change the numerical solver, the numerical errors will change and we need to retrain the model. And again, like we don't know what is the optimal neural network. There is some work to do there. That is reliable or interpretability. There is always some issues, but we need to be careful. And I wanted to illustrate the part of the physics that are unaccounted for. In a way that is true that the model doesn't account for some physics, but still it could give you useful information. We run this case is not physical. This is the Star Wars, this is X-Wing, Mach 20. So this is an aircraft that is flying very fast. And there are shock waves, there is heat transfer, compressibility. The model was never trained to capture those effects, but we can run the model, and we run the model in this case, and we make some predictions. But I want to highlight here is that we can always look at the confidence, and we can visualize the confidence of the model. So we run the model in this case, and in red you see the regions with the confidence is below 1%. So this model, this is a unique feature that other models don't have for this type of framework, that, yeah, you can run the model, but the model essentially telling you it makes no sense. Like I don't understand anything that is happening in this case. This doesn't look like anything I've seen before. So in a way, it could be very helpful. I mean, this might be a kind of extreme case because this case completely broke the model. But I think it's also very good to have control of when your model breaks. And this model, if it completely breaks, it will become very clear. So this is it, the conclusions. Again, you want to learn more about the technical part, just please go to these papers. So if you go to my website, we will have always there the last publications. But the idea was to use these simple building blocks and combine with some machine learning to be able to predict more complex cases. So with that, I'm done. I'll be happy to take any questions.
Thank you very much, Adrian. So let's start with our virtual friend. Here I see Black Hole Astro. Are you Tamara or Ignacio? And then I also see Pedrak. So do you have any questions? Pedrak? Leo? Okay. What about our here okay, let's see here in the audience. Yes.
Yeah.
Can you speak loud?
Sure, yeah. So it's fascinating research. My question has to do with transitions. So where a boundary layer detaches from the surface or like a transition to stall, since the training data set presumably is kind of steady state solutions, how well does the full model capture, you know, that type of, those type of like unstable regions?
Yeah, very good question. Let me go back to the, maybe I can do it this way faster. When I was showing the training data, these are the simple cases that we use for training. So first, one comment is like these cases themselves, because this is a turbulent flow, the solution is changing in space and time instantaneously. So they capture some kind of unsteadiness in the flow. And even one of the cases that we have, the last case is a turbulent flow that we are pushing in one direction and changing the direction. And that is statistically unsteady. And this case is actually one of the videos that I showed at the very beginning, although I didn't make the connection, is this, when I was showing this flow that you see here, this is actually one of the cases that we use for training, is the flow is changing direction as a function of time. So in a way, the model is able to capture some kind of unsteady effects, even locally or even over time. But still, what you mentioned is a good point. The model doesn't have anything to capture, if I come here, it cannot capture this kind of transition, laminar to turbulent transition. So when the flow is smooth and then suddenly it will separate, there is no mechanism for the model to capture that. And that probably, it doesn't work right now. We will need to extend the model to be able to capture that. It's not so simple. Related to separation, the model tends to capture separation okay. And the reason for that is because most of the large scales are resolved by the grid of large simulation. And the model only needs to account for the smallest scale. So usually, if there is something that is a large scale trend, the model will capture that. And then if the smallest scales is what is missing, and those are smaller than the typical geometry of the problem, then the model will do a good job.
Any more questions? Yes, Aris?
So thank you so much for the very clear presentation. And my question is related to the previous question. So it is a steady state thing, which means the classifier works only once. Am I correct in this? Or if the classifier is working all the time and updating its classification of the blending?
The classifier, so at each grid point, I get a classification that is changing in time. So if you can think of this, like the classification is a function of space and time. At each grid point, at each time, I have a classification, and that will keep changing. So it's dynamically updated all the time.
Yes, but for a particular regime, I'm saying, a particular regime, it is that. But when the flow changes character, you don't reclassify at this particular.
I'm reclassifying all the time at every time step at each point in space.
Okay, that's okay. I understand. But my next question is the classification, the blending scheme. Is it linear? What is the basis of the blending? Is it linear or is it some other way of doing it?
Yeah. Let me go because I have the formula here. Maybe that makes things simpler. So let me see which one is a good one.
I'm asking.
Okay, this one.
Okay, I see.
So this is how the classification here is called PI class. This is the probability of belonging to a given class. And my output is a linear combination of all the possible classes weighted with the probability of that class. So it's linear in the probabilities.
The linearity part I'm questioning because of I'm like your feedback on because it is a nonlinear system, and so I wonder if you feel that perhaps some other assumption that uses nonlinear sort of assumptions could work better.
Yeah, that's a good point, and probably what you are totally right. Like I'm assuming the following. Each building block, each prediction is fully nonlinear. So for example, if I have the first prediction will be fully nonlinear. The second prediction for the second type of flow is also fully nonlinear, but the way I blend them is linear. And that part, I did that because I saw that it was good enough, but I agree with you that probably the model will become better if I find a way of blending this solution in a nonlinear way. That probably would capture, I mean, it will definitely, it's gonna make the model at least better, but not worse. But for now, I did it because of simplicity. But I think that that's a good idea that we have been thinking about how we could do that in a way that is not very painful, because we need to do this training. And if they are non-linearly coupled, all these neural networks, it makes the training a bit more difficult. This one was a bit easier to train. So it was kind of practical.
Do you have any questions?
And my last comment is about the classification based on the similarity, as you say, of the input variables, as opposed to the predictions. Are you working to figure out if this classification scheme and the classification based on prediction errors are consistent or they are close? Because that's one of the limitations you mentioned, which I think is important, isn't it?
Yeah, that's important. So right now, the way it works, the classifier will always give me a classification. And that classification, in a sense, has no error. In the sense, like my model will always classify the flow, into 7 types. You can think of this. Imagine that my model can only classify cats and dogs. So it will, whatever I give to my model, it will always tell me 20% dog, 80% cat. Even if I give a car to my model, it cannot tell the difference. The difference, I get it from the confidence. That is kind of a separated block. So the confidence will tell me, so maybe the classification will tell me this is 20% a cat, 80% a dog, but then the confidence would be 1% because actually I'm feeding a picture of a car. So right now it's separated into 2 components. Maybe there is a way of doing everything together into 1 block and improve that uncertainty or make a better estimation of the uncertainty. And actually, if you or anyone has some ideas, let me know, because we've been trying to think about what would be the best way. I think that there is a lot of room for improvement actually in the way this is done right now.
Adrian, do you have some input with periodic orbit theory? Because here when Adrian talks about building blocks, it comes to my mind periodic orbit.
We haven't used periodic orbits. I suppose that probably that might be also an alternative to do. My main worry about the periodic orbits is that because this model is going to be deployed in cases that are very large Reynolds number, I will need to have periodic orbits somehow representative of high Reynolds numbers.
Yeah.
Or at least I will need how to rescale them. But it would be more elegant, actually. So if I could have a very nice collection of periodic orbits, the idea in a way similar is like I'm replacing periodic orbits by just a bunch of small simulations that I have done.
You enrich your library. Here you have a library of flows. I mean, you just throw more flows. Is right?
That's true. So that will improve in a way. I want to make.
Sorry.
I wanted to highlight that the library that we have now is 1 petabyte, and I didn't emphasize that, but to digest, the training is done with a GPU. To digest 1 petabyte through GPUs, there is a computer science component that I didn't mention that is non-trivial. But there was a full student 1 year trying to figure out how to move data from one point to the other of the memory in a way that we can do the training in a reasonable time. So extending the database, we want to do that, but it needs to come together with a better way of digesting the data. I don't mention that so much because it's a bit more boring. It's more like a data scientist job, but it's actually a bottleneck that we have. It's not so clear how to do that training.
Adrian, any comment? We cannot hear you. You are muted. Let me unmute you. Ask to unmute. We cannot hear you, Adrian.
Yeah, it's way above my pay grade. We use periodic solutions in very simple solutions of 3-dimensional Navier-Stokes in simple geometries. This is the real stuff. I have no idea how to do any of this. But as Francesco says, there might be a repertoire of nonlinear solutions for a given geometry and problem that might be useful, but I would be very happy if you knew how to do it, but I have no idea how to do it.
Yeah, I think actually it would be more elegant, as I mentioned before, if I could have more like clean solutions that they already capture the key physics.
Yeah, I mean,
maybe even,
when it works, it's powerful, but it's hard. I haven't seen it do it in real.
Ideally, I would actually like to reduce the data set, but optimize the amount of physics that they represent. I mean, that would be the best way, is that there is that component. I like it more in the sense that it's more about physics and about thinking what is the representative. I need to find like some templates of what I think it could happen in the flow. What are those and how do I find them in a systematic way that I can generate my training set? And I think that's actually the part
we use the same word. We call them templates. What's the most important spatiotemporal
So that question, and when I went to when I went to my variant and I mentioned limitations, to me, that's actually the main one of this model is what are these fundamental blocks? What are these templates? How many I need? Because the performance of my model is given by that. You cannot get more than the physics of the training set of these templates. So we also try to learn more about that and to see different ways that we could learn new templates and incorporate them.
Adrian, can I ask you a question about the machine learning part? Yesterday, I was having a discussion with a friend of mine that does machine learning. So you are using here a deep network, you know, with several hidden layers. I would like to ask you, based on your experience, is it good to have just once? Can you do the same things with one single layer? Or having these hidden layers does really make a change in the predictions? And how many do you need? You know, and also, what is the optimal architecture of the neural network? In the sense, can we talk about the topology design of the network that you know can be also optimized? You know, which I think, especially for this case, which is very complex, it would be nice to incorporate also in your optimization, also the topology optimization of the neural network. So I wonder what is your experience with these machine learning toolboxes?
Yeah, that's a great question. And my honest answer is, I wish I knew. I don't know if there is any theory that will really, maybe there is, and I need to learn more about people that they have more experience in the technical part of neural networks. In our experience, adding more layers help to improve the prediction. That's usually better than adding more neurons per layer. But at the same time, the networks, they become more difficult to train. So we try to find the balance, and it's completely empirical. I don't know. We start training with one layer, 2, 3, and we create many models. And we see how expensive it is to train the model and the performance. And then we find a sweet spot that is completely empirical, like, okay, this is a good balance between the cost of training, the cost of evaluating the network, and the accuracy. And we are also trying to understand other architectures that people now, for example, mention that they use transformers. They say that they're easier to train. I don't know if you're familiar with this new architecture, but this is the one that everybody's using for video prediction, text prediction, image prediction. So apparently you can also use that for regression, and we are trying to understand if that's useful or not. Again, I'm more a guy of physics and computational fluids. So to me, from that sense, I'm more a user, and I try to talk to people and learn from them what is the best way. Yeah, but many times they told me that they don't know.
You think, can you do a dynamical updating of your network by adding layers, adding neurons, or subtracting them based on some extra measure that you're gonna put in?
Yeah.
Do you think it's doable, or?
We do some of those things. We usually use the drop-off method, in which we have a network, it's a baseline, and we start dropping neurons and dropping layers in different combinations that are random, and we see if they matter or not. If they don't matter, then we simplify the network, that's better. If they matter, we have to keep that connection and that neuron. So we use those techniques in a way, because they're kind of established. But again, I don't think I can claim this is the best architecture or this is the best network, because it's more kind of an observation from the cases we try.
Thank you very much, Adrian. That was a beautiful talk and a very nice discussion. Any more questions from the audience and our virtual friend? Otherwise, you are all invited to have a pizza downstairs. Adrian, we wish you to be here now. We have
I would
some
like to
good
have
Italian pizza from Antico, but maybe in the future.
In the future,
so
hopefully.
I'll see you downstairs. Yes, thank you, Adrian. Bye, Pedrak. And bye all. So
thank you, Adrian. Bye-bye.
Bye-bye.